right. Well, it's 5:20 and no one's here yet, but I think I should go ahead and get started because we've got some material to cover and I'm making use of this time as well as some of the online time. So I just want to go ahead and get started. We haven't done in this online class, we haven't done much with chapter 27 yet. I mentioned some of the principles there or whatever, but that's about it. I did take the time to write up some keynotes about the concepts of magnetism that you have to understand. So you'll see them when I actually share my iPad. In fact, I'm going to go ahead and do that now. I'm going to share my iPad screen and you can see basically what I wrote. Of course, it's all in cursive. Hopefully that doesn't cause any problems. But you can also just get it from reading the book. Obviously, way more words, but I wanted to make sure I stressed at least some of the most important things that you should learn. So, for instance, it says evidence of magnetism was first found in a part of modern day Turkey called Magnesia. There was very specific types of rocks attracted to other rocks and repelled them too. Uh, since then, we've learned that the magnetic field can, or that magnetism can be treated like a magnetic field, not unlike the electric fields we studied in earlier chapters. The only difference, or the major difference, is that the electric field lines begun on positive charges, and then when they ran into a negative charge, they ended. So they actually had a finite existence, a finite length, and that sort of stuff. And it turns out with magnetism, we actually don't have a quote unquote finite length. We actually have closed loops so that they never end or start. In fact, they make complete loops except in transitory situations where they're like in transit from magnetic field existing to no magnetic field existing. We see that, for instance, in the surface of the sun. We also know that if you cut a magnet in half, magnets have a north end and a south end. If you cut them in half, you either cut them in half and you make two separate new magnets, each of which has a north and a south pole, or you've cut them in half in such a way that they ended up losing all their magnetism. In other words, there's no way we can take a magnet that has a north pole and a south pole, cut it in half, and then hold a north pole all by itself and hold a south pole all by itself. That's because, as best we can tell, magnetic monopoles do not exist, and in fact, we get from that a Gauss's law type equation for magnetism, but instead of it being the closed integral of B dot dA, which is, the left-hand side of Gauss's law is the closed integral of E dot dA, this is the closed integral of B dot dA is equal to zero, whereas the closed integral of E dot dA is Q enclosed over epsilon naught. So that equation, especially in differential form, makes a huge difference. Some other things you want to know is that magnetic field lines are like older Americans. They leave the north and enter the south. So that's just a mnemonic I made up to help my students remember that the magnetic field lines actually exit the north pole of a magnet and then re-enter the south pole of a magnet, and that they're closed loops. The Earth also behaves as if there's a bar magnet tilted at about 10 degrees from its rotation axis, and that bar magnet is in fact has what we call the north magnetic pole of the Earth is technically the south pole of that magnet, because obviously north poles of compasses point towards it, and they would only point towards it if they were attracted to it, and opposites attract. So the North Pole is attracted to a South Pole. So the North Pole of compasses pointing towards the quote unquote sort of north is because the North Pole is attracted to a South Pole, and that means the bar magnet inside of our Earth is actually a South Pole up near Canada. Actually, it's more like in the ocean right now between or headed towards Serbia from Canada. That's the latest I've seen, like 2022, I think, something like that. And it continues to move. And in fact, we know in history that it's reversed itself several times. You should also know that magnetic fields are created by currents and by changing electric fields. We should also mention that magnetic field strength is measured in Teslas, and that's the modern SI unit. But an older unit that we use as well is called the Gauss, and the Gauss is closer to the strength of the Earth's magnetic field. Excuse me. The Gauss is closer to the strength of the Earth's magnetic field, specifically the Earth's magnetic field near the Earth's surface is usually about half a Gauss. A Gauss, by the way, is a pretty small unit. The Tesla, for instance, is about 10,000 Gauss. So one Tesla is about 10,000 Gauss. and the Earth's magnetic field is about half a Gauss. And MRIs, like we use in medicine, generally are on the order of 1 Tesla in terms of the magnetic field strength. And then there's some other weird properties, like the magnetic fields do actually apply forces to moving charged particles. They don't apply any force to a charged particle that's sitting still. Yeah. But if the charged particle is moving with a velocity v, then the force is F is equal to Q times V, where Q is the charge times V. Remember that when you multiply a vector by a scalar, if the scalar is positive, you don't change the direction at all. If the scalar is negative, you flip the direction 180 degrees. So that's the key thing that you got to get out of this equation. F equals Q times V cross B means that first vector is either parallel to V in the case of positive charges, or anti-parallel to, or excuse me, anti-parallel to V, or parallel to V. It's parallel to V, the velocity, when the charge is positive, and QV is anti-parallel to V, the velocity, when the charge is negative. And then, of course, you have to cross that with a B, and we know I am so sorry. We know that cross products actually result in a third vector that's perpendicular to each of the two that went in it. So, in fact, the force vector that comes out of this law is actually perpendicular to the velocity vector and perpendicular to the magnetic field vector. With that in mind, you know that we can't speed up or slow down any charged particle with a magnetic field because the force always acts perpendicular to the velocity. So all it could do is make it curve or something like that. Uh, Magnetic fields also apply forces to current carrying wires. If you imagine a vector I times L, where it's the vector that whose length is the length of the chunk of current carrying wire that you're looking at. Ideally, it would be a long straight piece in a uniform magnetic field. If that's the case, then the vector IL would be parallel to the wire and would point in the direction of conventional current, and then you cross that with B to get the force. Or if you have uh, a varying shaped electric or wire carrying a current, you might have to break it up into small segments, DL, and you'd actually make IDL point in the direction of the conventional current, and then you cross that with B to get your actual force due to that little segment. And then, of course, you'd have to integrate it to find the net force as a result of all that. So that's another principle. Uh, you should go through your book and read about ferromagnetic, paramagnetic, and diamagnetic materials. Paramagnetic and ferromagnetic are fairly similar. Ferromagnetic, though, as you can see with the beginning of the word being ferro, just like Fe is a sign for iron, that means like iron. So ferromagnetic materials are materials that when you submerge them in a magnetic field, individual regions or domains within the actual chunk of ferromagnetic material, all of the little individual atoms or molecules making up that particular domain, which is a small part of the actual whole chunk of ferromagnetic material, all of them all align parallel so that their magnetic fields that the individual molecules or atoms are carrying actually line up parallel to the existing magnetic field that it's submerged in. If you get enough of those regions inside of the chunk of material that all align, then the more of those regions and the bigger those regions, the stronger the magnet of that magnetic material is. And when you remove that material from the immersed magnetic field that it's in, the magnetic field of the material stays. On the other hand, paramagnetic material behaves the exact same way, except when you remove the magnetic field that it's submerged in, the the magnetism of the object disappears, or the magnetism of the substance disappears. I think I want to recall that nickel is a paramagnetic material, but that's not my area of science, so I might be misremembering. By all means, let me know if you happen to know of any paramagnetic, diamagnetic, or ferromagnetic materials. Obviously, iron being one ferromagnetic material. And then finally, there's a diamagnetic material, and that one's really weird in that the little domains do the same thing as they do in the iron or in the ferro or the paramagnetic material, except they do it exactly the opposite. So if you submerge a diamagnetic material in a magnetic field, then its actual molecules make their individual molecules or atoms magnetic fields align, but they align exactly opposite the direction of the existing magnetic field. But when you do take the diamagnetic material out of the magnetic field, then the diamagnetic material no longer is magnetic. So it's like paramagnetic in that way, but it does create a magnetic field that's diametrically opposed to the existing magnetic field. Should also say your book introduces this as sort of a fact, and it's something you could readily do in one of your labs. In fact, you probably did it in the Faraday lab. But what we find is that a current carrying wire can create a magnetic field. The symbol we use for the magnetic field is B, and the magnitude of the magnetic field created by a really long straight wire is mu zero I over 2 pi r, where r is the distance you are away from the wire, and I is the current in the wire, and mu zero is called the permeability of a vacuum, and it's 4 pi times 10 to the negative seventh. Now that only gives you the magnitude of it a distance r away. But if you imagine, for instance, this was a current carrying wire and this sharp pointy point points the direction that the current's traveling, then what you do is you take your right hand like this and you put your thumb in the direction of the current, then your fingers curl around it like a grip on a bicycle or a grip on a motorcycle, and those fingers curl around in the direction that the magnetic field points. So you see your right thumb is pointing the direction of current, and now when you look at this, you see from your perspective that that should be a counterclockwise uh, rotation around the current carrying wire, and that's exactly what happens. So, for instance, if the wire has current coming out towards the camera, then right here above it, the magnetic field is to my right or your left. And then to this side, it's down. And then to this side, it's to the left, my left, your right. And then this side, it's up. So that's actually how the magnetic field behaves around the current carrying wire. So just remember, use your right hand rule. So you stick your thumb in the direction of the current like that, and then your fingers tell you which direction the magnetic fields go around it. And you can see it only depends on the R, the distance away from the wire. So what that means is you can imagine the magnetic field as a series of concentric circles that are counterclockwise around the wire. And for each radius, that is a particular magnetic field strength. So everywhere on that concentric circle has a magnetic field exactly the same strength. If I go out twice as far, then that magnetic field is going to be one half as strong. And if I go out three times as far, it's going to be one third as strong, so on and so forth. But it will be, like I said, given by the direction by the right hand rule. There's also a law called the Biot-Savart law, which we'll be learning in the next chapter, and I do plan on getting through that. We probably will not be able to get to it today, but the video I make tonight or tomorrow will certainly address that. And then there's also Ampere's law, which is another way of using something to calculate the magnetic field. That one is an equation that only works in really high symmetry for us to do what we want to do with it. So, for instance, just like Gauss's law, we use the closed integral of E dot dA to extract the E, the integrand from inside the integral equation. That was a surface integral. In the Ampere's law, we have a line integral, and we're going to extract the B out of it by having some understanding of the shapes of magnetic fields as a result of current configurations. Now, in this case, it's the closed integral of B dot dl, again, because it's a line integral, and the other side is equal to mu zero times the current enclosed within that closed loop. So again, we're going to learn more about that, and that's a bare minimum of what we'll get through this semester. I hope to get through chapter 29 and 30 as well, and I probably will, but it'll just mostly be sort of short and sweet, very much like the examples that I get to show you on the videos, and only like the examples that I get to show you in the videos. So, anybody have any questions? I now have a student here. So, how about you, Matt? You got a question, bud?
Hey, Professor. No, I guess you referenced when we did the integration of E dot dA that there was another very challenging integration
Hold on a second.
problem
I'm
as
having a
well.
hard time. Sorry, the volume wasn't up enough, so I couldn't hear
Oh,
you.
okay.
What did you
Yeah.
say? I'm sorry.
Well, back a couple chapters ago, you referenced when we were doing integration of E dot dA.
Right, right.
There was that was the most challenging integration,
Yes.
but for another one to be
Yep. And that's
moving in
that
the correct way. Is
Bio-Savart
that what you're
thing.
talking about? Okay, okay, all
Yeah,
right. So we're gonna
that's
great.
the ugly thing that's going to be so scary.
Okay, and so we're gonna get to that. Is that in this chapter when we're
It's actually technically next chapter. I'm doing such a short introduction to this chapter. We may actually touch on it at the end, but I'm not positive. But it'll definitely be in the next video or two that I send. I'll be showing you one. And it's pretty much because it's so complicated, you can use it to calculate the magnetic field along around a long, straight, infinitely long current carrying wire, and you can use it for very specific constructions. Like if you had a wire that was carrying a current and it was headed towards the origin, and then it stopped and hung a left turn and made a circular arc of a fixed radius, and then ran into the y-axis and then ran away from the origin, we can calculate the magnetic field at the origin with that really easily. It's nice. Or if you did that and then went up and then came back another arc of different radius and then another arc of a different, as long as you kept circles and radial lines, uh, the Biot-Savart law can be quite trivial. But when it's not that, it's really a nasty thing. But it's cool if you're a computer programmer because you can just type it up, a nice little program to make it integrate things, and you can calculate magnetic fields all day long.
okay.
All right.
And I think you answered the other question I had, but we're planning on getting through chapter 30.
Yeah, 30 is what I really want to get through. 31, I like to cover just because that gets us into the sort of the synopsis of all of Maxwell's equations and how they make electromagnetic radiation and how we can use that to express something called the Poynting vector. And we can talk about the electromagnetic spectrum. I've got a mnemonic for that. Great excess undermines various industries' Marxism rules. Which is homage to Rush Limbaugh, who developed me a lot in my life from watching him in politics. So I thought it'd be nice to say something that he would totally believe in. Us instructors are all communists.
Got it.
So that cool.
All right.
All right.
Yeah, sure thing. We better press them.
All right, no problem. I just wrote up all this stuff, and it's actually quite a bit of stuff. You came in afterwards, but you can see it's actually quite a bit of handwritten text. What I tried to do is pick out some of the most pressing facts that you had to know day in, day out while we're solving these problems. So I just decided to write them up, and I sort of read over them, even though I didn't really want to, but I couldn't imagine just saying they're in there and leaving everybody to do it. So we're done on that. Now I'm ready to work an example with some of these facts that I just expressed. So the first thing I'm going to do is consider one, how do you make a uniform magnetic field? We found, for instance, when we did electric fields, that a uniform electric field can be created by uh, uniformly charged positive plate put right next to a uniformly charged negative plate. And right in between those plates, we get a very uniform electric field, meaning it's literally a constant at every point as long as you stay away from the edges of the capacitor. The electric field has the same strength all throughout, and that strength is, of course, the charge per unit area divided by epsilon naught. That's the magnitude of the strength. Well, we want to know in what way do you go about creating a uniform magnetic field? Well, what you can do is you can imagine this round end right here being the south end of one magnet, and this round end being the north end of another magnet, and you can just put them really close to each other. And when you do that, the magnetic field lines will act as if they're coming from this north magnetic pole downward into the south magnetic pole, and everywhere between these two plates that are the ends of magnetic poles will be a very uniform magnetic field. So if you ever want a uniform magnetic field, that's the way you go about making it. I also said that you can create a magnetic field from current carrying wires are changing electric fields. That's something that Maxwell was able to discover and fixed his equations in such a way that now we get to call them Maxwell's equation, specifically because they were wonderful and they could do everything, but they missed one key term that made them all come together. And if you didn't have that key term, there was no way you're ever going to get electromagnetic radiation, which means we would have never had radios. We would have never had any understanding of how the sun's radiation gets to us, all that good stuff. So we're going to start from here now, just making use of some simple things like the magnetic field near a wire. I need to let you know that again, it obeys a right-hand rule. So again, if this is a current carrying wire and the current is going that way, you stick your right thumb in the direction of the current and then you wrap your right fingers around it. And all they do is tell you whether the magnetic field is counterclockwise or clockwise around the current carrying wire. If you go further and actually make, instead of a straight current carrying wire, you make a loop of current carrying wire, then each point on the circumference of that loop behaves exactly the same way as the long wire does. So you end up getting sort of a magnetic field that goes through the ring. And figure 2710 and 27.9 are pretty good figures to show you that picture. What I'm going to do now is go ahead and calculate some magnetic force stuff just so you can get a feel for it. So let's start off with a current carrying wire. I'm going to draw a current carrying wire like this, and we're going to say the wire is that thickness right here, and it goes on forever basically. But in physics, like I said, we will be dealing with things where we call wires infinitely long. And really, what we mean by the wire being infinitely long is that we're not going to get so far away from it that the distance we are away is 10 or more times bigger than the wire is. In other words, the wire is always going to be at least 10 times bigger than we are away from it. If we keep that, then we feel like doing pretty good at approaching or approximating an infinitely long wire. So in this case, let's imagine the current going downward. So that's our actual current and the wire going downward. Hopefully you can sort of see what I'm trying to do here. This is like a cylinder wire basically. Current is going downward this way. If we grab that with our right thumb pointing down and then we looked back over top of it, what we would see is that our fingers are now curling around, as seen from above. They're curling around in a clockwise fashion. So what we can do is we can imagine a plane, let's say a plane perpendicular to this wire. So to make that plane perpendicular to this wire, I'm going to run it straight this way and this way. Actually, I really wanted the program to make my lines even straighter there, but it didn't want to do it for some reason. So we're doing that and that. That's a line coming in and out of the page towards me on the plane that's perpendicular to the wire. And then there's another line that's on the plane perpendicular to the wire, and it's going left and right. So hopefully that picture of those two red lines and imagining them on a plane gives you some idea of the three-dimensional aspect that we're trying to get from this. So what I'll do is I'm going to go ahead and make this like it's a full three-dimensional object, specifically a three-dimensional plane, something like that. And that's our actual plane. So I drew that just to give you some feeling for what I'm about to draw. So what we found out is when we looked from above, so we imagine our eyes like this, we're looking from above, we found that when we looked from above with our right thumb pointing down, our fingers of our right hand go in a clockwise fashion. So what that means is I need to draw a clockwise circle around this particular object. So I'm going to put some base points on this just to give me an idea roughly where it should be. And now I'm going to attempt to draw a ellipse to represent the actual circle that I'm drawing. So that should be an ellipse that is basically a representation of a circle, but it's a three-dimensional, well, it's a two-dimensional representation of a three-dimensional representation of a circle. So what I'm trying to do now is I'm going to make sure that everybody knows this is behind the wire. So to do that, I did all this, and now I'm going to go back and draw those lines back in like so. And you can see that the magnetic or that the blue line is now laying on this plane, and we got to now remember that it's supposed to be clockwise. So what does that mean? That means if we step back behind the wire back here, okay, then the magnetic field will point to our right. If we step to the right of the wire, then our magnetic field will point out of the page. If we step in front of the wire, our magnetic field will point to the left. And I'm trying to make all these roughly the same length because they're all the same distance R away. So keep that in mind. But also, if we step to the left of the wire, then we get the magnetic field pointing out back into the page. So that's the actual directions of the magnetic field at various locations. If you happen to want to know where the what the magnetic field direction is here, that would be like that. If you wanted to know it here, it would be that. So you can see it's just sort of tangent to that circle at every point. That's what the magnetic field of a current carrying wire looks like. And in fact, if you wanted to know what that is, let's say the current I is equal to 5.00 amps. That's a pretty significant amperage. And if we say that this distance from here to here is, let's say, 5.00 centimeters, then the magnetic field strength at on that particular circle will be B equals mu zero I over 2 pi R. So the mu zero is 4 pi times 10 to the negative 7 Tesla meters per amp. This is just another constant like the epsilon zero. The epsilon zero we called the permittivity of free space. It was the permittivity of a vacuum. This is called the permeability of free space or permeability of a vacuum. Now I'm going to take it and multiply it by 5.00 amps, and then I'm going to divide that by 2 pi times the radius, which would be 0.0500 meters because it has to be in meters. And when I do this calculation, you can see I'm basically going to get, oops, calculator should be on. That would be helpful. I'm going to get 2 times 10 to the seventh times 5, and then I'm going to divide that by, I already, by calling it 2 times 10 to the seventh, I already calculated 2 pi of it. Now I'm just going to divide that by 0.05, and that gives me a rather ginormous magnetic field strength. One, two, three. Oops, no wonder. 2 times 10 to the negative seventh times 5 divided by parentheses 0.05. I evidently didn't hit the negative last time, so I knew something was wrong. This gives me, in fact, a 2 times 10 to the negative 1, 2, 3, 4, 5, a 2 times 10 to the negative fifth Tesla magnetic field. That is about zero point 0.2 Tesla, excuse me, about zero point 0.2 Gauss. So it's not even as strong as the Earth's magnetic field, even though that's a 5 amp current and we were only 5 centimeters away. So you can see that it's going to be kind of weak, the magnetic field, because 4 pi times 10 to the negative seventh is a really, really weak constant. Any questions on that one?
No, no question.
Okay. Now, another neat thing that's helpful to do is once you have that wire, you can sort of learn a little bit how wires are affected by currents. And I've already given you that equation, but just to remind you, it's F is equal to I L, and I'm treating that like a vector. Your book doesn't do this, but I am. I'm treating that like a vector. So what we do is if we have a length of wire whose length is L, what we do is lay a vector right along that length of straight wire so that it's the whole length L that's in the magnetic field. And then we put the head on it so that the arrow is pointing in the same direction as conventional current. And then we just do the cross product with the B to get the magnetic field. So to give you an idea what that's like, let's imagine that we have a uniform magnetic field. This is B is equal to, and let's use a big magnetic field. Let's use 1 Tesla. 1 Tesla magnetic field is really big. That's comparable, like I said, to the strength of a MRI that we might use when we screw up our knee or hip or something like that. Uh, Now what I'm going to do is take a chunk of wire and I'm going to imagine it doing all sorts of crazy things, but then all of a sudden it goes straight through this little bit of wire, so or through this little bit of magnetic field. So what I'm imagining here is this is the chunk of wire that is going to feel a force as a result of this magnetic field. And I'm going to say this length of wire is L equals, let's say, 20.0 centimeters. And that's the length of the magnetic field in, or excuse me, the length of the wire that's in the magnetic field. All the stuff above it and below it doesn't matter because it's not being affected by the magnetic field at all. I will also say that this angle right here is going to be 60.0 degrees. The reason why I do that is because remember, if we have a cross product, A cross B, the magnitude of that, which we can express as just absolute value bars around the A cross B, is the magnitude of A times the magnitude of B times the sine of the angle between them when they're tail to tail. So if this is A and this is B and they're tail to tail, then this is the angle theta we're talking about. Okay? So my idea was to actually take this current, which I'm going to say is going to be 5 amps, and I'm going to say the current I equals 5.00 amps is going this way. Because of that, I'm going to imagine a vector that represents that wire like this. So you now see that I have a wire 20 centimeters, or excuse me, a vector 20 centimeters long. That's 20 centimeters long, and it's tilted at an angle of 60 degrees from the magnetic field because we saw that the magnetic field did this and that this angle was 60. So really all we have to do is we can imagine sliding this red vector up, and now that's where that red vector is, and you see that now they're tail to tail. In other words, you do see that I sort of imagine sliding this red vector up to where the blue vector is now, and you see that they're tail to tail, so you know the actual angle between them that's relevant to the formula is 60 degrees. So now all I have to do is calculate the force. F is equal to IL cross B as the formula, but the magnitude is going to be I, which is 5.00 amps, times L, which is 0.200 meters, times the magnetic field strength, which is 1.00 Tesla, times the sine of 60.0 degrees. So we should have 3 sig figs on everything. And obviously 5 times zero point 0.2 should be 1, and then times 1 should be zero point 0.1, or excuse me, times 1 should be 1, and then times sine 60. So if you look at this, we get 5 times zero point 0.2, which is 1, times 1 times the sine of 60, and that gives me square root of 3 over 2, which is 0.86603. So 0.866. Here's my extra digits, 0.3, and that comes out in newtons. So that would be the force on that, but we need to understand what the direction of that force would be. Now, the way we do cross products, and there's a lot of different ways, by the way, but one of the ways you can do cross products is you can hold your hand, your right hand like this, where your thumb is perpendicular to your index finger is perpendicular to your middle finger, and your middle finger is perpendicular to your thumb as well. So you hold them like that. Now, the middle finger, because we're doing a cross product, the middle finger can actually move. What we know is that when the two parts of a cross product are parallel, when A cross B, for instance, when you're trying to calculate that, and the A is parallel to the B, then that's going to give you zero because obviously the sign of zero is zero. So we don't really want this middle finger being at 0 degrees because that's going to give us zero, nor do we want it being at 180 degrees because that's going to give us zero as well. But anywhere between 0 and 180 is acceptable. So what you're trying to do is take this index finger and put it in the direction of the first vector, which for this formula was I times L. And then you take your middle finger and you point that in the direction of the magnetic field. So on this one, I had the wire and the current going up and to the right. So I hold my index finger up and to the right. Now I can orient my hand any way I want to, long as my finger stays up and to the right at that 60-degree angle. But what I need it to be able to do is to move around so that my middle finger can now point in the direction of the magnetic field, as you see that it does now. See that this is literally my middle finger is parallel to the blue magnetic field, and my index finger is literally parallel to the black wire. And when I look at that, I see my right thumb is pointing into the page. So that's actually what happens. The direction for this is into the page. Can you follow that?
Yep, I got it. That was covered in 27 also.
Oh, good deal. Good. Yeah, that's normally like the hardest part about the 242 and the 202 course, and all of them is basically that right hand rule that comes up so much. But once you learn it once, it pretty much always applies because it's almost always a result of the cross product. Another way you can do it, by the way, if you like that better, is I sometimes think of this as one straight bone, even though it's not, of course, but I think of it as one straight bone that becomes sort of an axle, and that axle is going to be the first vector in the cross product. And then I lay my that one long bone parallel to the vector, and I can move it all these different ways as long as this stays parallel to the first vector. But what decides how I orient my hand is in which direction the other vector points. So if the other vector, for instance, points over this way, I need to be able to curl my fingers towards it. I can't do that right now, so I have to turn my hand around this way, and now my fingers can curl so that they now point in the same direction as the second vector. When I do that, now I see, oh, the force is up. So that's another way of looking at it. Hopefully, one of those techniques will help you. Now
So I
that,
guess I do have a question.
go for it.
So the angle between the current length vector
Hmm.
and the magnetic field really is irrelevant for the direction of the force, right?
Yes, that's irrelevant for the direction, but it's relevant for the magnitude.
Correct. Yeah.
Yep,
Yeah.
yep.
Got it.
Good job. Actually, that's really good that you stated that. I kind of wish I had told my students that before. I don't think I ever have, but in light of you asking it, it tells me that's something that they concern themselves with, so I probably should have. Uh, all right, now that we have that, I'm going to show you something else kind of neat. You might wonder, what do two parallel currents do? If you have two wires next to each other and the currents are parallel, are they attracted to each other? Do they have no effect on each other, or are they repulsive to one another? What about if they're opposite? So I'm going to walk us through that little problem as well. So what we're going to do here is we're going to imagine one wire that's going to be, say, blue, and here's the other edge of that same wire. Okay, and what I'm going to imagine with this one is that it has a current I1 going upward. I'm going to say I1 is 5.00 amps. And now I'm going to draw another wire. And this wire, I wanted to use the app to actually draw a really straight line there, and I did not do that. Now I'm going to draw another one. So this is the other wire, and let's say it has a current of I2 equals 7.00 amps, and they're parallel because you see they're both going up. I'm going to also assume that this distance dead center between them is 10.0 centimeters. And what I'd like to know is what is the force on wire 2 due to the current I1 slash wire 1. In other words, you can sort of say it's wire 1 causing a force on wire 2, or wire 2 causing a force on wire 1, or you can just say it's the current. I wanted to cover all that. It's pretty normal for us to speak like the wire is doing it when in actuality it's just the current. But the way we're going to do that is I'm going to answer a few questions. For starters, I'm going to say, number one, what is the direction of the B field? Remember, B is the symbol we use for the magnetic field. B field caused by I1 at wire 2. So, in other words, what you need to use here is your right-hand rule to tell me in which direction the magnetic field would be pointing at the black wire as a result of the blue wire. And some directions are right, left, up, down, into the page, out of the page, stuff like that. Can you figure that out yet, Matt? If you can't, don't worry about it. It's not that big a deal. You just heard it, but go for
Yeah, no, I'm sorry. I missed the question. I was
it. No problem.
distracted.
What I'm thinking here is current I1 going through the blue wire has created a magnetic field around the blue wire. I want to know at the location of the black wire, which is, you can imagine these as if they're both laying on a single tabletop, that is this graph paper, which direction is the magnetic field due to 1 pointing at wire 2? Can you tell me that?
Which direction is it? I mean, it's pointing directly towards the black wire, correct?
The magnetic field for wire 1 is pointing towards the black wire. Is that what you're saying?
Well, I mean, I'm just using the I'll get my video going here, but
Yeah.
I just holding
You're
the
doing the right thing now. Yeah, gotcha.
yeah. So it's going counterclockwise
Okay.
into the page. Does that make sense?
So remember it's counterclockwise around. So you're right about that. You're sticking your thumb up, and what you want to think now is you want to physically picture yourself getting up over top of the wire and
Mhm.
looking down. Now that you're looking over top of the wire, imagine a wire just to the left of the wire, or excuse me, in this case it'd be just to the right of the wire, and tell me which direction the magnetic field is right there. So the wire's here, and we want to know right here where's.
Yeah, I mean, it seems like it'd be pointing directly towards the
Okay.
black wire.
That's okay. That's perfectly normal. That's exactly what happens. What I'm going to do is I'm going to remind you that we can draw a little plane perpendicular to the wire, and that might help us a little bit.
Oh, yeah, yeah, I got it.
You
Right.
see it now?
Yeah, so it's pointing directly into the page.
Excellent. Good job. Good job. Yeah, so you did know it. Gotcha. That's awesome. So
Yeah.
what we're going to do now is we're going to say the magnetic field at wire 2 is this magnetic field. And since it's pointing into the page, you can either put an X there or you can put a circle with an X inside of it. Either one of those will do. I don't like how that turned out, so I'm going to be obsessive compulsive about it, of course. So there's my circle, and there's my magnetic field line going right into the page. So I'm going to say into, whoa, Nelly. It does not like it when I do that. Into the page. So we now have that. Now I want to use question 2. Since F is equal to IL cross B, in what direction does the force on wire 2 due to wire 1 point? So now you're doing yet another right-hand rule. You have that the magnetic field at the black wire is into the board or into the page. You have that the current is going up, and you need to use your right-hand rule to do IDL cross B. Can you figure out whether that's force is up, down, left, right, up and to the left, up and to the right, down and to the left, down and to the right, or any of those types of directions?
So
Again,
it's the force from the black wire towards the blue wire. So the
remember,
current's going up.
yep. So IDL should go up.
And so the fingers are pointing into the page.
It
And
looks
so
like
the
you're
thumb
doing
is
it right.
pointing to the black or to the blue wire.
Exactly. That's exactly right. So parallel currents do attract one another. The force points to the left, which is toward wire 1. So in other words, parallel currents attract. So that's a new thing. Now all we have to do is calculate what actually is that length. And what I'm going to do is I'm going to assume that this length of wire and the other length of the wire is 40.0 meters. And they're only 10 centimeters apart. And from that, I'll calculate the force. So step 3, the force is going to be, I already know the direction. All I need is the magnitude. And the magnitude is ILB sine theta, where theta is the angle between IL and B. Do you happen to know? I think you. I mean, you literally did everything right just now in the video I just watched you. So you had everything right. Can you tell on that figure that you came up with your hands in the air? Can you tell the angle between the IL vector and the B?
I have to think for a second. The
No
IL
problem.
vector and the B field was into this, so it would be 90. Yeah.
Yes, exactly. 90 degrees. Excellent. So we got to calculate the magnetic field first for the wire, the blue wire. So I got to do that. But I know that the wire for the black wire, the current is 7.00 amps. That's the current experiencing the magnetic field. And the length of that black wire is 40.0 meters. And the magnetic field B has got to equal mu 0 I1 over 2 pi r. So that's 4 pi times 10 to the negative 7th Tesla meters per amp times 5.00 amps for current 1 divided by 2 pi times 0.100 meters. And that magnetic field should be, the 2 pi cancels out with a 4 pi, leaving 2 times 10 to the negative 7th times 5. And now I'm just going to divide that by zero point 0.1, which is the same thing as multiplying by 10. And lo and behold, I get 1.0 times 10 to the negative 5th Tesla is the magnetic field. So I'm now going to put 1.00 times 10 to the negative 5th Tesla as the magnetic field strength. And then I'm going to say times the sine of 90 degrees because you were good enough to figure that out. So now I take 1 times 10 to the negative 5th, multiply it by 40, and then multiply that by 7. and that gives me 0.002800 newtons. So that's the actual force on the current carrying wire as a result of the other current carrying wire. So we've got a couple things there that are important. One, parallel currents should be attractive to each other, and you can work out again if you try flipping the I2 upside down and make it going downward and leaving the I1 pointing up. You'll find that they are repulsive, and you should find that the magnitude should be exactly the same. It's just they're trying to get away from each other when they're opposite currents. Any questions on that one?
Nope.
All right. So there's some neat little questions as well. For instance, there's a little question like this. You can imagine having a current carrying wire right here. We can connect a battery and then we can run the wire down here, and we're going to allow that wire down here in the bottom. We're going to allow that to actually have a current going this way. And we'll say, just to make it a little easier, we'll say something crazy like this is the only resistor in the circuit, and this resistor is 60.0 ohms, and we'll say that this battery is 12.0 volts. So we can now calculate what this current I is from Ohm's law. V equals IR. We know that I should be equal to V over R, so we're going to get 12.0 volts divided by 60.0 ohms, and 60, of course, is 5 times 12. So that might help us as well. And you can see that the 12 cancels out with the top, and I end up getting 0.200 amps. So that's the current going through there. So you could say it's 200 milliamps, for instance. But here's the neat part. What I'm going to do is tell you that there's actually a magnetic field that actually exists around this bottom wire, but pretty much only the bottom wire. So what I'm going to do is I'm going to say, here's a magnetic field, here's a magnetic field, here's a magnetic field, and then here's a magnetic field. And it's pretty much uniform is what I'm trying to get across here. And that magnetic field is B. And specifically, what we'd like to know is what is B uh, if we say that the force acting on this particular piece of wire is actually downward. So I'm going to say F is downward, and it's going to be 3.48 times 10 to the negative 2 newtons downward. I am going to find out what B is now. Okay, so for starters, what I want to do is figure out which direction is the force. I drew an arrow here, but I was just trying to show you hypothetically the possible direction could be down, it could be up, or whatever. But now that you know I've got a current going to the right in that wire in the bottom, can you tell me which direction the magnetic field is going to cause a force on it?
Yeah, it's going to be up.
Okay, that's right. So IL would be pointing to the right, and we have to orient our hand so that the magnetic field can point into the board. So that means that way, and then my right thumb is pointing up. So yes, you're absolutely right. The force is up, and it's that magnitude. Now, out of curiosity, the current over here on this side is down. Which direction is the force on that little piece of wire? Even though it only goes up to like this part, just like this one only goes up to that part, which direction would the magnetic field or would the force be on that part on the left?
Be to the right.
Okay, so I and then DL. Yes, you're absolutely right. That one's to the right. So I'm going to say F is to the right there. And then the one on the left, I think you can see would be to the left, right?
Yes. So
Okay.
should the current on the is the current traveling downward for both vertical segments?
No, no, that's your instructor being mentally compromised. Let's say that. I don't know what's going on. I don't know
Just
why I drew it
trying to
down,
figure
but
out how that comes in.
that was magic. It was magic. It's like
Yeah.
echinacea. It can cure you. So, thank you. All right. Now that we have all that, and you actually passed with flying colors all the direction stuff, which is supposed to be the hard stuff. So now all we have to do is use F is equal to I L cross B as magnitude, because we already figured out the direction. So as magnitude, it's going to be F equals I L B sine theta, but you can see that clearly the I times L is to the right and the B is into the board. That means theta is 90 degrees. So you don't even have to do any trig functions. We're just going to say the magnitude F is equal to ILB. Now we can plug in the numbers we know. We're going to say 3.48 times 10 to the negative 2 newtons is equal to 0.200 amps times the length of the wire, which oddly enough I left off, but I'm going to say that is 20.0 centimeters, like that. So I'll put choose, or I'll have to write it in meters, of course. 0.200 meters times B. So now all I got to do is solve for B. And when I solve for B, I get 3.48 times 10 to the negative 2 divided by zero point 0.2 times zero point 0.2, and that gives me 0.8700. Actually, that last one didn't have to be underlined. Tesla. So that's the magnetic field strength for that force to be a result given that current configuration and that length of wire. Any questions on that one?
Nope, no question.
Okay. Now we're going to do one that's a little bit more difficult. And what I'm going to do is I am going to draw a wire in which a current is running upward. I'd like to use the tools of this note-taking app. And the tools I'm going to use are that straight line. And now I'm going to imagine this making a curved line, a actual semicircle like that. That's supposed to be a semicircle, but this made it into a parabola because it's a jerk. I did not want that part to happen. So we're going to say what? This is 1, 2 and a half, 1, 2 and a half. So I'm going to go up 1, 2 and a half and do roughly there. And 1, 2 and a half would be roughly there, and 1, 2 and a half would be roughly there. So now hopefully I can draw it in such a way. Nope, it's still going to make it a parabola because it's a butthole. So now I'm just going to draw it by hand. So that's our semicircle, and then like this. So what's going on here is I have a current I. Uh, the stupid thing keeps jumping to taking over and trying to draw a neater line when I don't want it to. So let's call that the current. Let's call this the radius. And let's imagine that the magnetic field lines are basically, or the magnetic field specifically, is going out of the page for us, and it's a uniform magnetic field. So we're sort of imagining these all pointing in the same direction and being more or less equally spaced apart, and they even have these out here so that every part is really covered. Okay, what we want to calculate is the total force on this current carrying wire. Specifically, we're really only worried about the arc because I think you can tell that this part from here to here has a length L, as does this part here. And if you actually compute the force on the right hand side, go ahead and try that in your head. The force on the current that goes to upward on the right hand side, uh, you try to pick that direction. I'm getting ready to draw it out. So the force here would be this way. And now you try to pick out the force direction for the current on the left hand side where it's going down. I think you'll see that that force goes to the left. So these two forces, since they only depend on the magnitude of the magnetic field, the length L, which is the same, and the current, which is the same, we know for a fact that these two parts are going to cancel out. So we're left with just calculating the net force on just the semicircle at the top. So in this case, we're going to have to use a differential form of the IL cross B. That differential form is going to be dF is equal to I dl cross B, like that. Okay, so what I'm going to do is I'm going to just imagine a little segment of wire. And in fact, I'm going to picture this as if we've got it on an XY coordinate system. So here's my X axis, and here's my Y axis. And what I'm doing is imagining that I sweep through an angle theta, and then I allow that line that is a distance r long, I'm going to allow that line to squiggle over a little bit by an amount delta theta or d theta. Let me draw it in here like this. It's going to be kind of small, so I'm going to zoom in this way. So I'm going to say this line right here differs from the other line by an angular amount given by d theta. Then this little piece of arc right here has a arc length ds, which is equal to r d theta. And therefore, I can call this little segment, this is going to be my dl, and it's going to be r times d theta, and it's specifically going to point in a tangential direction like that. Now, technically speaking, that angle or that vector as a unit vector is a vector called theta hat. So I could, in principle, just write theta hat right there and we'd be done. But in order to do that, you sort of have to understand what theta hat is. Now that I've gotten it, notice you can zoom in it to look at it in the bigger sense, but I'm going to zoom back out and it'll be smaller. Just remember that the arc length is ds. That's going to represent our dl along the wire, and it's given by rd theta, but it has to point in the direction of the current, so I drew it up and to the left. Now I'm going to draw a separate diagram so we can analyze exactly what's going on there. This diagram I'm just going to show like this, and I'm going to say that obviously this angle is theta, and obviously this angle is d theta. But what I need is this direction is our x direction, and this direction is our y direction, and this direction would be what we normally call the r hat direction. And I can work that out, and I'm going to, just so you'll know. But then perpendicular to the radial line is a vector that's this way, and that's the theta hat one that I was just talking about. So that's our theta hat, and that's our r hat. We can see that this is theta, and from symmetry, we know that r hat is behind theta hat by 90 degrees, just like x-axis is behind the y-axis by 90 degrees. So that means this angle over here is also theta. Because of that, we can now write that r hat, which you don't need at all, but I'm just showing it to you. You would normally say it's the hypotenuse of that r hat vector, but since it's an r hat vector, the hypotenuse is 1, so you're going to say 1 times cosine theta I hat. And then this component over here is the y component. We already did the x component, which is right here. It's going to be 1 times sine theta j hat. And in fact, that's exactly right. R hat is cosine theta I hat plus sine theta j hat. Similarly, you can think of this vector and this vector as components of theta hat. And when we do that, we get theta hat is equal to the hypotenuse, since it's a hat, is again going to be a 1. But this time the x component, notice it's pointing in the negative direction, and it's given by sine. So I'm going to say negative sine theta times I hat. And then the y component, notice that's given by 1 times the cosine of theta. And that is multiplied by the j hat vector. So theta hat is really negative sine theta I hat plus cosine theta j hat, just for you to know. You didn't have to actually do that. In fact, we could have just put it in recognizing exactly what its direction is by analyzing the individual ds. So instead of putting ones in there, I just put ds's in there and I'd still get the same result, but it's nice having it in terms of theta hats and r hats, which will come up in cylindrical and spherical coordinates later. Now that I have that, I just need to apply my formula. My formula says that f is equal to the integral of df, which equals the integral of I dl cross b. So I know the current is I, so and I know it's a constant, so I'm going to go ahead and pull it out in front. And I'm going to say the integral of dl, well, the dl we found was r d theta, theta hat, and that has to be crossed with B. And in this case, the magnetic field B, by the right hand rule, we see that the X and Y being oriented like they are means the Z is coming out of the board. So the magnetic field is in the K hat direction, and we'll just call it B K hat. So that is the actual cross product that we got to do. And it seems really, really scary, but it's not that bad. And it's definitely not as bad as the Biot-Savart law. Now, the good thing about a cross product is like it's a dot, it's also like a dot product in that it's what we call a linear operator. So we can bring out all those. If we had multiple terms, we can bring out the separate terms. But also when we have multiplication by scalars, we can bring the scalars out in front so that we only have to do cross products on actual vectors. So I'm going to bring out the I and the R out in front. The B, which is also a constant, I'm going to bring that out in front too. And all I'll be left with is d theta. And I'm going to integrate, of course, from theta equals 0 to pi of theta hat crossed with K hat. So notice I've done everything. I've brought all the scalar parts out in front, and I'm just left with a vector cross producting with a vector. So we can actually cross product that all we want, or we can plug in theta hat and then work out exactly what the cross product is. But if you think of theta hat as pointing up and to the right, and K hat is coming out of the board, you can see automatically by turning my hand this way, say, and having the K hat come out this way, we can see that the thumb is pointing in the radial direction. So we know right now that theta hat cross K hat is really just R hat. But if you didn't see that, that's okay. All we have to do is compute it. So if I wanted to compute it, I could just say cosine theta, or excuse me, negative sine theta I hat plus cosine theta j hat. If I did a cross product of that with k hat, I just have to take each term. So I'll say negative sine theta times I hat cross k hat plus cosine theta times j hat cross k hat. That's how all this cross product's going. If you look at a 3D coordinate system that is really right-handed like it's supposed to be, then you'd see that this is X, this is Y, this is Z. That means that this is I hat, this is J hat, and this is K hat. So when you do I hat cross K hat, see if you can figure out what that is now. I hat cross K hat,
I hat cross
K
A
hat.
hat.
Can you tell me like what direction? You don't need to know the number right now, but if you can figure out the direction, you're golden.
Well, it's got to be perpendicular to both.
Exactly. So
So
that
it's
leaves
got to be along the x plane, I guess, directly to the right.
to the left.
To the left. Okay.
Yeah. Again, you're going to take your index finger and stick it out of the page like the X is. You're going to take your middle finger and stick it straight up like the K is, and then your right thumb is pointing to the left now. So you see that this is in fact what we would call negative J hat. What about J hat cross K hat?
J hat cross K hat. So J hat is my pointer finger.
Yep. And
K
K
hat
is your
is
middle
my
finger.
middle finger. So it's got to go negative I hat.
I got
Right?
positive I hat. Are you using your left hand by mistake?
No. So J hat's going to the
Or to the
right.
right, and K hat is up.
Oh, yeah. I'm
Okay.
using the wrong finger. Yep.
Good to hear. 9 times out of 10, when someone get the wrong answer, it's because they forgot that they're right-handed and they're using their left hand.
Yeah.
So that one does turn out to be the I hat direction. So that's really all we have to do. You can write it that way, and now you'll see you're going to get sine theta J hat plus cosine theta I hat, which is in fact R hat. So that's how we're going to continue to proceed with this integral. We got R times I times B, and we're going to have the integral of. Now, remember, as us in physics, we write things to the right of d theta. They're still integrated though. So I'm not getting out of integrating that. The d theta, I can move to the far right, and now I'm going to put my result, which is sine theta j hat plus cosine theta I hat times d theta. That means we're going to get, let's call this BRI because I like that order better. And I'm going to do the integral of sine theta d theta and multiply that result times j hat. And I'm integrating it from theta equals 0 to pi. And then I'm going to do an integral of cosine theta d theta. And that one's times the I hat. And that's from 0 to pi as well. But notice here, if you look at this, the vector at different places is going to have x components and y components. But if you look at the x components or y components from these forces, you'll see that the y components continue to help one another, whereas the x components on the right half cancel out with the x components on the left half. So you expect that I hat term to go to zero by symmetry of the actual diagram. Now we're going to see it actually happen. The way we're going to see it is by computing the integral. So I've got b times r times I. The derivative of sine is cosine. So the integral of cosine is actual sine. The integral of sine is actually negative cosine. So I'm going to say negative cosine theta, and that's going to be evaluated from 0 to pi. And I'm going to say plus sine theta, and that's going to be integrated from zero or evaluated from 0 to pi. And of course, I have a j hat here and an I hat here. Now, cosine of pi is actually -1. So negative of -1 would be +1 minus, now cosine of 0 is 1, so that's +1 -1. That's going to give me, in fact, actually, I better be careful with that. and make sure I actually did the right thing. The derivative of negative cosine is negative sine. So the integral of, no, the derivative of cosine is negative sine. So the derivative of, yeah, just wanted to make sure I got the right function there. So now when I integrate this, I get the negative cosine of pi minus negative cosine of 0 times j hat plus sine of pi minus the sine of 0. We know that both of those are 0. So the I hat term disappears, which is consistent with the symmetry that I just mentioned to you. Now the cosine of pi, like I said, is negative 1. So a negative of a negative 1 is a positive 1. And then minus a minus, the cosine of 0 is 1. So I'm going to say plus plus 1. So I end up getting 2. So the actual answer is 2BRI J hat. And that's the total force acting on that semicircular loop. You can tell that's not necessarily the funnest integral to do, but that's probably the second hardest integral you'll do the whole 2 semesters of this course. Any questions on that one?
No questions. I will probably have to go back and review that one.
No problem. And actually, your book explains it a way that's physically ingenious, but mathematically pretty straightforward. I tried to be mathematically ingenious, but not physically ingenious. So between the two of the way the book did it, the way I did it, and maybe the ways you'll find in Khan Academy or something did it, you'll probably find some way that feels a little more comfortable to you. But just, find that way and use it.
Okay.
All right.
Yeah,
Uh,
I guess a question I have is why can't we just simplify the integral and call DL uh, uh maybe it's simpler for me to just call DL or to call L R sine theta and go
yeah.
from
You sort of can, and that's sort of the way the book did it. Is they sort of broke up the force into a I component and a J component. In other words, an X component and a Y component. And then he argued that clearly the X component is going to go to 0 because on the right hand side the X components are positive, on the left hand side they're negative. So they're going to, and they're symmetric, so they're obviously going to be equal but opposite. So they're going to disappear. And he ends up doing it without actually having to evaluate a cross product too terribly. So that might actually, I mean, you probably will understand it better now that you've seen this way than you would have if you just read it out front. But just reading it out front, you can get a pretty good understanding of it as well. You just probably would feel like, man, I don't think I would have came up with that on my own.
yeah, okay, got it.
Okay. And that's about it. I'm going to make some more videos. I might make some tonight, but I'm definitely making some more tomorrow and again Thursday. That should finish up 28, 29. We've almost done everything in 27 now. I've only got a couple more things that I want to do, and I know you got to probably split pretty soon. But I'm going to do those couple things, and then I'm going to go into 28, and just a couple things from there. Same thing with 29, and same thing with 30. So you did get my email that I sent out today, right?
Yes, I did. One question.
Yes.
I think you mentioned last week that you had a video that didn't get recorded. Did you end up re-recording that and
Yes.
pushing it out? Okay.
Yes,
All
I
right.
did. I
Then
can
I'll
even
see.
tell you which one it is if you want to wait for just a second, because that would be very helpful to you to know. I'm
Yeah,
pulling up
sure.
my YouTube channel right now. Uh, it was okay, not that one. Let's see. It was making vectors, no. Always calculate torque, no. Angular kinematics, omega, using calculate center mass, examples of charging battery. Uh, Kirchhoff's solving 2 circuits in an introduction. That's the one. It says Kirchhoff's laws solving 2 circuits in an introduction to RC circuits. I think that was the one that I had to go back and redo.
Yep, I see.
And I'm trying to look if to see if it was another one too. I knew there was two of them that I did, but I wanted to make sure I didn't mix up one for the other. The other one was the power lighting GFCI, but I think that was the one that did get recorded correctly.
Yeah, I think so. I think I was in that one.
Yeah, okay. That's cool. Yeah, so I'm about 99% sure it's the one that I said was Kirchhoff's law solving two circuits.
Okay, sounds
All
good.
right. All right. Have a good one, Matt. Appreciate you coming.
Yep. Thanks. Yep. See you next time.
Have a good day. Bye bye.